40 amp Square-D QO GFCI 220 circuit breaker is suitable for a 1 and 1/2 horsepower pool pump with a full load amperage of 9.2 amps at 240 volts. GFCI circuit breakers require some headroom above the full load amperage of the load to account for starting surges and transient loads. The 40 amp breaker provides sufficient margin for the pump's full load amperage. Rewiring the motor to 120 volts is not recommended in this case, as the full load amperage would increase to 19.2 amps. The 20 amp GFCI 120 volt breaker would not be sufficient for this full load amperage, and a larger breaker would not provide GFCI protection. It is recommended to use the 40 amp Square-D QO GFCI 220 circuit breaker for the 1 and 1/2 horsepower pool pump. It provides the required GFCI protection and sufficient capacity for the pump's full load amperage. Always follow proper electrical codes and regulations when installing and wiring electrical equipment. The installation should be performed by a qualified electrician. It is important to verify the correct wire size and conduit size based on the pump's full load amperage and the distance to the circuit breaker panel. When choosing a circuit breaker, several factors need consideration to ensure safety and proper operation of the connected equipment. Firstly, the ampere rating of the circuit breaker should be appropriately sized for the load it is intended to protect. This is crucial to prevent nuisance tripping while still providing adequate protection against overcurrents and short circuits. Secondly, the voltage rating of the circuit breaker must match the voltage of the electrical system in which it is installed. Using a circuit breaker with an incorrect voltage rating can lead to equipment damage or even hazardous situations. Thirdly, the interrupting rating of the circuit breaker is a critical specification that indicates the maximum fault current the breaker can safely interrupt. This rating should be higher than the potential fault current at the installation location to prevent the breaker from failing during a short circuit. Fourthly, the type of circuit breaker, such as standard, GFCI, or arc fault, should be selected based on the specific application and the protection requirements of the connected equipment. GFCI breakers are essential for circuits serving wet locations like bathrooms and kitchens, while arc fault breakers provide protection against dangerous arcing faults. Fifthly, the listing and certification of the circuit breaker by a recognized testing laboratory, such as Underwriters Laboratories or Canadian Standards Association, ensures that the breaker meets established safety standards and performance requirements. This is an important factor to consider when selecting a circuit breaker to ensure its reliability and safety. When dealing with electrical installations, understanding the concept of full load amperage, or FLAW, is crucial. FLA refers to the amount of current a motor draws when it's operating at its rated horsepower and voltage. It's a key parameter used for sizing conductors, overcurrent protection devices, and motor starters. To determine the FLA of a motor, you can typically find it listed in the motor's nameplate. This value represents the maximum current the motor should draw under normal operating conditions. If the nameplate isn't available, you can refer to the National Electrical Code, NEC, tables, specifically tables 430.247, 430.248, 430.249, and 430.250, which provide standard FLA values for different types of motors based on their horsepower and voltage. When selecting conductors for a motor circuit, the NEC requires that the conductors have an ampacity of at least 125% of the motor's FLA. This ensures that the conductors can handle the continuous load of the motor without overheating. Similarly, the overcurrent protection device, such as a circuit breaker or fuse, must be sized to protect the motor and the conductors from overloads and short circuits. The NEC provides specific guidelines for sizing these devices based on the motor's FLA and the type of motor. For example, for a standard motor, the overcurrent protection device should typically be sized no larger than 250% of the motor's FLA. Motor starters, which are used to control the starting and stopping of motors, must also be selected based on the motor's FLA. The starter's contactor must be rated to handle the motor's inrush current, which can be several times higher than the FLA during starting. Understanding and correctly applying FLA values is essential for ensuring the safe and reliable operation of motor circuits. Ignoring these values can lead to overheating, equipment damage, and even electrical hazards. Remember to always consult the NEC and follow manufacturer's instructions when working with motor circuits. Now let's delve deeper into the selection and application of ground fault circuit interrupters, commonly known as GFCIs. These devices are crucial for protecting people from electrical shock hazards, especially in wet or damp locations. Firstly, it is important to understand how a GFCI works. A GFCI constantly monitors the current flowing in the circuit's hot and neutral conductors. If there is an imbalance of 5 mA or more between these two conductors, it indicates that current is leaking to ground, potentially through a person. The GFCI quickly trips, interrupting the circuit and preventing a dangerous shock. Secondly, GFCIs are required by the NEC in specific locations to protect people from electrical hazards. These locations typically include bathrooms, kitchens, garages, outdoor areas, and anywhere else where water is present or where people may come into contact with grounded surfaces. Thirdly, there are two main types of GFCIs. GFCI circuit breakers, which are installed in the electrical panel and protect the entire circuit, and GFCI receptacles, which are installed at individual outlets and protect only that outlet and any downstream outlets. Fourthly, when selecting a GFCI, it is important to choose one that is listed and certified by a recognized testing laboratory such as Underwriters Laboratories or Canadian Standards Association. This ensures that the GFCI meets established safety standards and performance requirements. Fifthly, GFCIs should be tested regularly to ensure that they are functioning properly. This can be done by pressing the test button on the GFCI, which should cause it to trip. If the GFCI does not trip when the test button is pressed, it should be replaced immediately. Sixthly, when installing a GFCI, it is important to follow the manufacturer's instructions carefully. This will ensure that the GFCI is properly wired and will provide the intended protection. Seventhly, GFCIs are not a substitute for proper grounding. Grounding provides a path for fault current to flow back to the source, which helps to trip the circuit breaker and prevent a dangerous shock. GFCIs and grounding work together to provide comprehensive protection against electrical hazards. Eighthly, GFCIs can sometimes nuisance trip, especially in older homes with wiring issues. This can be caused by a variety of factors, such as faulty appliances, loose connections, or excessive leakage current. Ninthly, when troubleshooting a GFCI that is nuisance tripping, it is important to first identify the cause of the tripping. This may involve testing appliances, inspecting wiring, and checking for any signs of water damage. Tenthly, if you are not comfortable working with electricity, it is best to call a qualified electrician to install or troubleshoot GFCIs. Electricity can be dangerous, and it is important to take precautions to protect yourself from shock hazards. Now let's explore the implications of rewiring a 240-volt motor to operate at 120 volts. This is a common question that arises when dealing with motors, and it's important to understand the considerations involved. Firstly, it's crucial to determine if the motor is designed for dual voltage operation. Some motors are designed to operate at both 240 volts and 120 volts, while others are designed for only one voltage. If the motor is dual voltage, it will have a wiring diagram on the nameplate that shows how to connect it for each voltage. Secondly, if the motor is dual voltage, rewiring it from 240 volts to 120 volts will change its operating characteristics. Specifically, the motor's full load amperage, or FLO, will increase. This is because the power consumed by the motor remains the same, but the voltage is lower. Since power equals voltage times current, a lower voltage means a higher current. Thirdly, when rewiring a motor from 240 volts to 120 volts, it's essential to ensure that the circuit can handle the increased current. This means that the conductors, overcurrent protection device, and any other components in the circuit must be sized appropriately for the new FLA. Fourthly, if the circuit is not properly sized for the increased current, it can lead to overheating, equipment damage, and even electrical hazards. Therefore, it's crucial to perform a thorough electrical calculation to determine the correct size for all of the circuit components. Fifthly, in the specific case of the pull pump, rewiring the motor from 240 volts to 120 volts would increase the FLA from 9.2 amps to 19.2 amps. This means that a 20 amp GFCI breaker, which is the largest available for 120 volt circuits, would not be sufficient to handle the motor's full load amperage. Sixthly, using a breaker that is smaller than the motor's FLA can lead to nuisance tripping, as the breaker will trip whenever the motor draws its full rated current. Seventhly, using a breaker that is larger than the motor's FLA can be dangerous, as it will not provide adequate protection against overloads and short circuits. This can lead to overheating, equipment damage, and even electrical hazards. Eighthly, in this situation, the best course of action is to use the 40 amp GFCI breaker on the 240 volt circuit. This provides the required GFCI protection and sufficient capacity for the motor's FLA. Ninthly, it's always important to follow proper electrical codes and regulations when installing and wiring electrical equipment. This will help to ensure that the installation is safe and compliant with all applicable standards. Tenthly, if you are not comfortable working with electricity, it's best to call a qualified electrician to perform the work. Electricity can be dangerous, and it's important to take precautions to protect yourself from shock hazards. Now let's talk about the National Electrical Code, or NEC, and its relevance to electrical installations. The NEC is a comprehensive set of standards and guidelines for the safe installation of electrical wiring and equipment in the United States. Firstly, the NEC is not a law itself, but it is often adopted by state and local jurisdictions as part of their building codes. This means that compliance with the NEC is legally required in many areas. Secondly, the NEC is updated every 3 years by the National Fire Protection Association, or NFPA. This ensures that the code remains current with the latest technological advancements and safety practices. Thirdly, the NEC covers a wide range of electrical topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It provides detailed requirements for everything from residential wiring to industrial power systems. Fourthly, one of the key principles of the NEC is to protect people and property from electrical hazards. This is achieved through a variety of requirements that are designed to prevent shocks, fires, and other electrical incidents. Fifthly, the NEC is organized into chapters, articles, and sections. Each section provides specific requirements for a particular aspect of electrical installation. Sixthly, the NEC uses a system of tables and calculations to determine the correct size for conductors, overcurrent protection devices, and other electrical components. These tables and calculations are based on factors such as the load current, voltage, and ambient temperature. Seventhly, the NEC requires that all electrical work be performed by qualified individuals who are trained and knowledgeable in electrical safety practices. This helps to ensure that the work is done correctly and safely. Eighthly, the NEC also requires that all electrical installations be inspected and approved by a qualified electrical inspector. This provides an additional layer of safety and helps to ensure that the installation complies with the code. Ninthly, the NEC is a complex and comprehensive document, and it can be challenging to understand and apply. Therefore, it's important to have a thorough understanding of the code before attempting any electrical work. Tenthly, if you are not familiar with the NEC, it's best to consult with a qualified electrician or electrical engineer. They can help you to understand the code and ensure that your electrical installation is safe and compliant. Let's consider wire size selection for electrical circuits. Choosing the right wire size is crucial for safety and performance. Firstly, the ampacity of the wire must be sufficient to carry the expected load current. Ampacity refers to the maximum amount of current a conductor can carry continuously without exceeding its temperature rating. Secondly, the NEC provides tables that list the ampacity of different wire sizes and insulation types. These tables take into account factors such as the ambient temperature and the number of current-carrying conductors in a raceway or cable. Thirdly, when selecting a wire size, it's important to consider the dating factors that may apply. Dating factors are used to reduce the ampacity of a wire when it is installed in conditions that can cause it to overheat, such as in a hot environment or with multiple conductors bundled together. Fourthly, the NEC also requires that the voltage drop in a circuit be limited to a certain percentage of the supply voltage. Voltage drop occurs when the voltage at the load is less than the voltage at the source due to the resistance of the conductors. Fifthly, excessive voltage drop can cause equipment to malfunction or operate inefficiently. Therefore, it's important to select a wire size that is large enough to minimize voltage drop. Sixthly, the NEC provides formulas for calculating voltage drop based on the length of the circuit, the load current, and the resistance of the conductors. These formulas can be used to determine the appropriate wire size for a particular application. Seventhly, in addition to ampacity and voltage drop, it's also important to consider the mechanical strength and durability of the wire. The wire must be able to withstand the physical stresses of installation and operation. Eighthly, the type of insulation used in the wire is also important. The insulation must be suitable for the environment in which the wire will be installed. Ninthly, when selecting a wire size, it's always a good idea to consult with a qualified electrician or electrical engineer. They can help you to determine the correct wire size for your specific application and ensure that the installation complies with the NEC. Tenthly, remember that using the wrong wire size can be dangerous. Undersized wires can overheat and cause fires, while oversized wires can be unnecessarily expensive and difficult to work with. Selecting the appropriate conduit size is important for protecting electrical conductors and ensuring safe installations. Firstly, the NEC specifies the allowable fill percentages for different types of conduits. These fill percentages limit the amount of space that can be occupied by conductors within the conduit. Secondly, the fill percentages are based on the number of conductors in the conduit and the type of conduit being used. Different types of conduits, such as rigid metal conduit, electrical metallic tubing, and flexible metal conduit, have different fill percentage limitations. Thirdly, the NEC provides tables that list the allowable number of conductors of different sizes that can be installed in various sizes of conduit. These tables can be used to determine the appropriate conduit size for a particular installation. Fourthly, when selecting a conduit size, it's important to consider the dating factors that may apply. Dating factors are used to reduce the ampacity of conductors when they are installed in conduit with multiple current-carrying conductors. Fifthly, the NEC also requires that the conduit be properly supported and secured. This helps to prevent damage to the conduit and the conductors inside. Sixthly, the type of conduit used must be suitable for the environment in which it will be installed. For example, rigid metal conduit is often used in areas where it is subject to physical damage or corrosion. Seventhly, the NEC also specifies the minimum bending radius for conduit. This is the minimum radius to which the conduit can be bent without damaging it. Eighthly, when bending conduit, it's important to use the proper tools and techniques. This will help to ensure that the conduit is bent smoothly and without kinks. Ninthly, when selecting a conduit size, it's always a good idea to consult with a qualified electrician or electrical engineer. They can help you to determine the correct conduit size for your specific application and ensure that the installation complies with the NEC. Tenthly, remember that using the wrong conduit size can be dangerous. Overfilled conduits can overheat and cause fires, while undersized conduits can be difficult to work with and may not provide adequate protection for the conductors. In summary, when working with electrical systems, always remember that safety is paramount. Consult the NEC, local codes, and qualified professionals to ensure all installations meet the required standards and are performed safely.